Welcome to Calculus. Today we will investigate solving related rates problems that deal with spheres and cones. We'll take a look at two examples, one of each. Our first example has to do with a spherical snowball being rolled in fresh snow, causing it to grow so that its radius increases at a rate of 2 inches per second. How fast, we want to know, is the volume of the snowball increasing when the radius is 7 inches? We'll start off by identifying our variables. We should really think about what geometric situation we're looking at. It's really a sphere. So this is a spherical diagram representing that snowball. And when I think about the measurements that I would take to define a sphere, really it's down to just the radius. It's that length from the center of the sphere out to the edge of the sphere. So I'll put definitely one of my variables is going to be r, the radius. And then based on what the question's asking, how fast is the volume, I know one of my other variables is going to be volume. In fact, just those two, radius and volume. So when I think about then my rates that I've got to include there, it would definitely be the change of rate of the radius, with respect to time, so dr dt. And in fact, I'm given that as a value here. Its radius increases at a rate of 2 inches per second. So I'm going to define that as 2 inches per second. And then definitely what I'm trying to find is dv dt, the rate of change of the volume with respect to time. That's my question mark. And then I am on the lookout for any specific data about measurements. So I'm told that we're interested in the rate of change of the volume, specifically at the instance when the radius equals 7 inches. So I'll notate that as well. Now I've got my variables, I've got my rates, and I've got my data, specific data all organized and written out. I want to find an equation that will relate my two variables, the volume and the radius. And we don't have to look far in geometry to find Archimedes' famous equation. The volume of a sphere is 4/3 pi times the radius cubed. So I've got my equation. I now need to take the derivative of both sides so that it becomes applicable for discussing rates. So let's take derivative of volume with respect to time and also derivative of that whole right side, that product 4/3 pi r cubed with respect to time. So on the left, what that gives us is dv dt equals, so I've got several constant coefficients there. 4/3 pi is a constant coefficient, that whole product. And then as I take derivative of radius cubed, I'll bring the 3 power down as a coefficient and multiply times r to the power of 2, 1 less than 3. And then times this differential, the change in radius with respect to time. So now I can see that the rate that I'm looking for, dv dt, is solved on the left. So all I need to do is substitute in values for the radius and for dr dt. So let's make those two substitutions. What we see is 4/3. In fact, what I'm going to do is notice as I move to the next step that I've got a 3 divided by 3 cancellation. So in terms of my equation, it's now 4 pi times the radius. So the specific radius measure we're looking at is 7 inches. And that is squared. And that is times dr dt, which is again 2 inches per second. So we've made our substitutions. At this time, I just need to multiply out and simplify and see if we can come up with an answer. So I do see I've got a square 7 inches. So that's going to be 49 times 4 times 2. So 49 times 8. Let's multiply that out. So that's going to be 392 pi. And then for my units, I have from the inches in blue, inches squared, times the inches in purple will be inches cubed over seconds. And if I think, just to consider, is that consistent with the rate I'm trying to solve for? That would be a volume changing per second, and that's exactly what I'm looking for, is dV dt. So this first example looks at a sphere. Let's take a look at a cone, a conical situation. So here we're imagining a conical paper cup. So a nice cup that you might get at the water cooler is 30 centimeters tall. So it's a rather large paper cup with a radius of 10 centimeters. The cup is being filled with water so that the water level rises at a rate of 3 centimeters per second. We want to know at what rate is water being poured into the cup when the water level is 4 centimeters. So I would start by, again, drawing the figure just so we can see what geometric solid we're trying to describe. So it's a cone that's inverted as a water cup. And like we did with our sphere, what we want to do is say, what basic measurements would I need to take in a cone to find really its volume? So I see that it's got this central height. I'm going to call that h, which goes from the apex of the cone to the base of the cone and hits at a 90-degree angle. I also have the radius of the cone, which is from that center of the circular base to the edge of the circle over on the cone's side. So basic measurements here involve r, which is the radius, and h, which is the height. And then just looking at the question and what it implies, I'm being asked at what rate is water being poured into the cup. That's a measurement of volume. So I've got my variables listed there. What I want to also say is then what rates are involved here. So I definitely see that I have a rate that involves the water level rising. That's going to involve my height. So that rate would be dH dt. And that is a constant value of 3 centimeters per second. That's given in the question. The question itself, what I'm trying to answer here is what rate the water being poured into the cup. That is going to be described by dV dt. So that is what I'm trying to solve for. What's the rate of the volume as time changes? And then I do have a specific piece of information. I'm told that the specific height we're interested in is 4 centimeters. So I've got my information laid out and organized. What I need to do now is write an equation that will relate my variables. So again, I go to geometry to find the equation for the volume of a cone, and that was given by the volume equals a third pi r squared. So it's a third times the area of the base. It's a circle, pi r squared, times the height. And that is all fitting together. My basic variables are fitting in a single equation. My challenge at this point is I now have more than 2 variables. And when I go to differentiate in a moment, I'm going to have to deal with a third rate that I don't really have described, the change of the radius with respect to time. And so what I'd like to do is see if I can call the radius something in terms of the height. And really it goes back to our diagram. We're told some specific measurements for the full cone. The height of that cone is going to be 30 centimeters. The radius of the full cone is going to be 10 centimeters. Now, as I'm seeing here, this figure that's created by the radius, the height, and the side of the cone is a right triangle. And so from geometry and similar triangles, if I were to watch water fill up, my radius would be proportional to whatever height it's at. And so what I can say is that the radius has this constant ratio of 10 to 30 of the height. And that gives me an equation, r equals a third of whatever the height is. So even as like the water level is very short, that ratio is still intact. Whatever the height is, the radius is a third of it. Up to the full height of the cone at 30 centimeters, the radius is a third at 10. So what I'll do here as I make my substitutions with various things, in fact, before I differentiate, I want to make this substitution in the equation. Wherever I see r, I want to write instead 1/3 h. And I'm going to make that change before I differentiate. So the equation I'll be working with is volume equals 1/3 pi times parentheses 1/3 h squared times h. And that we can even further simplify. So I see I've got a third factor on the outside on the left and a third being squared. So a third squared is 1/9 times another third on the left would be 1/27 pi. And then h squared times h would be h cubed. And that is the equation that I want to work with when I take the derivative. So we're ready to do so now. We'll bump it up so we can see it there in the center of the screen. So I'm going to take this equation, volume equals a 27th pi h cubed, height cubed. And I want to take the derivative of both sides with respect to time. So right away I get the rate dv dt, which is what I'm looking for, equals the derivative of a 27th pi h cubed. So my constant coefficient there is going to be 1/27th pi, and then times the derivative of h cubed. So that's going to be 3h squared, and then dh dt. So now we've taken the derivative, I'm ready to substitute in values for the height and for dh dt. So my next step would be 1/27 pi times 3, and I've got h for my specific value of 4. We had pulled that out of the equation, so I'm going to substitute that in 4 centimeters squared. And lastly, I'll make substitution for dh dt. That was given to us as 3 centimeters per second. Once I've made those substitutions, I want to simplify that statement. So I see that I've got a 3 and a 3 in a numerator level, so that's 9, which will combine with my 1/27th to be 9/27, or 1/3. I've also got a pi there, and then I've got 4 squared, which is going to show up as a numerator of 16. I can go ahead and multiply that. And then for my units, I've got centimeters squared in red times centimeters over seconds, which will give me the final unit of centimeters cubed over seconds, cubic centimeters per second. And again, when I check that to see, does that match my rate that I'm trying to solve for, the change in volume per time, so cubic centimeters per second works well. Thanks for joining for this investigation of solving related rates problems involving a sphere and a cone. Thanks for joining. See you soon.